let's try and talk through this somewhat quickly. Okay, I got people referencing energy a lot, and energy is fine, but entropy is going to contribute to your overall energy. So I wouldn't look at entropy as energy in itself. Look at how it's going to contribute to that. And so one of our discussions within this is that we're talking about, let's see, was it the previous slide? Of course, I have the wrong button. Is it this one? We're looking at these more or less microstates. So the possibilities for where our particles can possibly exist. Okay? So we're looking at possibilities, the way that I like to think about it, because possibility is a very nebulous term, though if you saw that Marvel movie with the ant dude, the most recent one, I think, and he enters a probability storm and all these things. Yeah, okay. Maybe you don't remember that. Okay, you remember that? Yeah. Okay. That's effectively what's happening, is you're creating more possible states in those kind of scenarios. That's that probability thing. But that can be really nebulous to think about, and that's where I would push to motion. Right? If I look at liquid versus gas, which of those has more motion? The gas. Why? It goes back to the properties of liquids versus gases. Liquids occupy their volume. What do gases occupy? The volume of the container. So it changes your possible motion states. Right? So your gas typically has a much higher entropy than your liquids or solids. What happens in the next one? They're both gases. Right? And we say, well, the temperature is changing, so therefore the energy is changing. Again, think less on the energy and more on what's happening to the motion. If I heat it up, what happens to the motion? They're moving faster. They're going to be in more different spaces. We have more probabilities. Right? We move to the last one, 2 moles versus 3 moles. Again, same phase. Right? No temperature defined, which should imply that they're at the same temperature. That can be dangerous, but that should be our implication. Which one's going to have more possible motions?
3 moles.
3 moles. I'm not running any calculation. I'm just saying there's more particles there. The more particles I have, the more possible locations those particles could be. That was this system. We're looking at 1 particle, low entropy, versus 6 particles, higher energy. The number of the particles changes your possible states, okay, or what we would call microstates. Kind of, sort of? Okay. So what's fun about this is that we don't have to do any calculations. Oh, crap. Okay. Well, not yet. Okay. We've got some tables on here that can then reference our kind of entropies, and we can look at the entropy of varying substances, okay, and different, well, in this case, it's not varying substances, it's varying phases. If we look at the entropy for the solid, it's at 3.4 units. Let's not stress about the units yet either. Okay, what happens as I continue to increase the temperature? The entropy increases. Okay? What happens when I transition from the solid at 0 degrees to the liquid at 0 degrees? Did my temperature change? No, it's still 0 degrees, and yet what happened? The entropy increased rather drastically. Why? The solid to liquid transition allows for more motion. That more motion is going to suggest a higher entropy. As we continue to increase the temperature, you'll note that again the entropy starts increasing. And then all of a sudden at this 100-degree one, we see a massive jump in entropy. Right? The liquid to, or solid to liquid was about 20 units. If we look at the liquid to gas, math, somebody help me out, 110 units. Right? That's a massive leap. We don't see any leaps like that in any other system. Why? Well, what's the difference between a solid and a liquid? What volume does a solid occupy? Its own. What volume does a liquid occupy? Its own. Which means, relatively, are we seeing a significant change in entropy there? No. The motion, yes, increases a little bit, but it's not increasing that much. When we jump from liquid to gas, the volume is now going to change drastically. The volume is going to be, or our phase is going to be dictated based off the volume of the container, not the volume of the substance itself. Which now means I have way more places that my individual particles can exist. Okay? I'm going to see a wicked jump in the entropy values. Okay? As we continue to increase the temperature of the gas, look what happens. We revert back to smaller increases in entropy. Why? Because we aren't seeing that much of a change, again, via our temperatures. It's the phases that dictate the larger aspect. Okay? Which becomes important for us when we're looking at overall reactions, because what we want to consider is what are the largest effects? Well, the largest effect that we're going to see is in the phases, which is why when you go back and look at the previous question, the very first question, or the very first part of that question that you looked at phase transitions. That's where we had the largest differential. Okay? We've got pictures that are representing these low and high energy states, entropy states. Okay? And now that we have numbers, of course, what can we do with numbers? We can do math. So we can now go through and look at particular reactions, and we can start to do math. Except to do math, what do I need to know? Yes, I would need an equation, but what do I have to do with that equation? Plug in values. Do I know any values for the entropy for these? No. So does that mean I can't do any calculations? I can still run a calculation. It's just going to be relatively simple. This calculation is just going to be predicting what should happen to the entropy. When I cross this reaction, should the entropy go up? Should it go down? That's still a calculation. You're just doing it without numbers. So, talk at your tables, figure it out. Do they increase or decrease in each reaction? Okay, so what did we notice? What do we think? What should happen to the entropy for the first reaction? Why should it increase? Okay. The first observation that you're hopefully noticing is looking at the phase changes. When we run across this chemical reaction, we're starting with a liquid and a gas, and we end with two gases. Okay. On its surface, that would suggest that our entropy should increase. We're taking a liquid and we're now providing it more space to roam in the gas state. Okay? What else could we show or postulate to suggest that the entropy should increase? Okay? If we're looking at the first side of the equation, we could try and do this, well, I got 2 and 13. I would argue it's really only 13. Why would I ignore the 2?
Because it's a liquid.
Because of the phase. Okay? So I'm looking at 13 particles of gas on the left-hand side of the equation turning into 18 particles of gas. 18 particles is more particles, though more particles means more entropy. So we're getting lots of things suggesting that the entropy should increase for this. Okay? If we were going to run a calculation, what we would need to do is determine the change in entropy. So change, we would use a delta symbol for. Right? S is our symbol for entropy. And if we ran that calculation, what would we expect the sign of our change in entropy to be? So as a guess, there's only 2 signs possible. It's either positive or negative. If it increased, do you think that's a negative value? No, that's a positive value. Okay? Our change in entropy is going to be calculated the same way as we calculate anything else. It's products minus reactants. If the products have more entropy minus our reactants with lower entropy, that's going to be a positive value, not a negative value. What happens with the production of cement? Don't all shout out and answer at once. Just because I'm playing with the trash can doesn't mean be quiet. Why should the entropy increase? What do you see? Okay? We're starting with a solid and we're ending with a gas. Okay? That phase transition is a huge signifier for looking again at a positive value for our entropy. Kind of, sort of? Okay. As I kept starting into and then fading back from, because I forgot the sequence of slides, okay, of course, now that we know that we could predict these things, we need to now quantify them. And so if we're going to quantify them, we would need a formula. That formula we actually just talked through. Right? It's our product entropies minus our reactant energies. Does this formula look familiar? Yeah, it should look really familiar. It should look almost identical to the one we used when we talked about enthalpy. Because it really is. Okay? We talked through all the symbology behind it when we talked about enthalpy, so we okay with this? Think you know how to use this? Yeah, we got a couple people saying, yeah, I know how to use it. Okay, which then means, what do we got to do? Prove it. Okay? Same deal at your tables. Go through and set it up. Okay? For using calculators, okay, so I just heard someone seem to be upset about not having a calculator. I don't have a calculator either, and I can still estimate the values. Okay? Yes, they're estimates. They're not perfect, but they can at least get you in the correct ballpark that we can have a conversation about those estimates. As we set this up, resume recording. Okay, we do want to remember our formula where we're starting with our products first. So CO2 is a 213.8 joule per mole Kelvin. Right? That N in my expression has to show up. That N for CO2 is 8. I'm pulling the coefficient from that substance. The units on that would be mole. Why is that useful? The units can cancel out. So that way when I go through to do the addition, I have the proper units to track this. 10 moles for the H2O because that's the 10. Okay, so that N is different for each of the species within our expression. Okay. What do I now do? That's the sum of my products. What do I want to do next? Okay. I love how you phrase that. We'll come back to that one in a second. Let's find the sum of our reactants. When we go through and look at our reactants, it was 231. I need to provide a little bit of space, different spacing. 231.0, again, joules per mole Kelvin. The coefficient for that one was 2 moles. So we could look at that canceling. I want to do the sum. So again, I'll add, where'd it go? Our O2, 205 joules per mole times Kelvin. Did I do that one right? Yeah. And then its coefficient. What was its coefficient? That's our 13. My spacing is a little bit off. 13 moles. Okay. And now all I gotta do is run my calculation, right? What do I do with the two values I'm gonna get? Because this is gonna give me a number, a sum, and this is gonna give me a number. Okay, top minus the bottom. This becomes really, really important because what I've seen lots of students do with their work, here's where we'll bust out the estimation. Okay, it's going to be pretty crude estimation, sorry. 8 times 200, 1,600. Okay, I meant to have that be in purple. So about 1,600. Plus 10 times 1,900, 190, sorry. So it becomes 1,900, right? Okay. And then people will go, well, minus 2 times 200 is 400. And then they'll say plus, and this becomes the issue, 13 times 200 is about 2,600. Okay, and then they'll enter that into the calculator and they'll get a number. The number they'll get will be wrong. Okay? Why is it wrong? We have to recognize the distribution of that minus sign. So if you're going to write it out in this way, you have to make sure you distribute the subtraction calculation all the way through to ensure that that's not a positive, that it's a negative. Okay? Because it's the quantity being subtracted. It's the sum of the products minus the sum of the reactants. That minus sign has to be distributed. Okay? And if you struggle with that, you're not alone. I struggle with that all the time. That's mean. So what I would go through and do personally is I would take my sum of my reactants, 1,600 plus 1,900, 35, 3,500. My 400 plus my 2,600 is 3,000. Now I run my calculation, and my answer comes out to be ballpark 500. So I don't distribute that minus sign because I'm confident I'll screw it up. Why am I confident I'll screw it up? Because I've had lots of practice doing it. And in that practice, I have recognized that the more times I do it, the more times I distribute that minus sign incorrectly. So I create systems that prevent me from doing that. You may have other systems. Parentheses are lovely to use as long as you remember to use them. Some people do, some people don't. So it's going to come down to whatever strategy works for you to be consistently correct. Okay? Let's push on this a little bit further. According to my calculation, we come out as a positive value. Did we say we should come out as a positive value? Yeah, cool. What value did you actually come out with, not estimated? 471.4. I would argue my estimate was pretty rock solid. Okay? Kind of makes sense? You guys get it? Okay. Our positive calculation means our entropy increases. A negative change means it decreases through the course of the reaction. All right, so in this reaction that we looked at, we predicted that the entropy should increase just based off of inspection. Looking at those things and saying, well, we've got a phase change. We've got numbers of particles. All of those things would suggest the entropy increases. Okay? Then we actually calculate it and prove it. Kind of, sort of? Question was asked on Monday that I thought was an awesome question. So awesome, in fact, I assumed it was a typo, and I had to go look it up. Which entropy would you expect to be larger, a liquid or a gas? A gas, right? And not only should the gas be larger, we would expect it to be significantly larger.
Every single gas.
And even the other gases, yeah. What's going on with that? C4H10 has a pretty large entropy in comparison to all the other gases. There's no difference in moles. It's the exact same number of moles. You might be saying something else. The atoms involved. Does that matter? Yeah, because now that structure, if we look at C4H10, is a longer, floppier structure. So as it flops, that's more possible states for the individual molecule. If we look at oxygen, CO2, and H2O, there isn't any flopping going on with those. Those are now based just off of the raw phase. So we can look at other effects that contribute to entropy beyond just our phase transitions, the numbers of moles, and what was the other one? I already forgot it. The atoms isn't one we addressed until just now. Where did it go? all the way back here. Temperature, thank you, I forgot that one. Okay, we're looking at phases, we're looking at temperature, we're looking at the number of particles, and we can throw in a really hard one, the complexity of the molecules that you're studying. Okay? The complexity of the molecule becomes a really challenging one to nuance. Why? What do you have to be able to do to evaluate the complexity of the structure of a molecule?
Be able to understand the structure.
You have to be able to draw the structure, which means what do you have to be able to do?
Living structures.
Lewis structure. And if we look at Lewis structure, C4H10, what's your center atom? That one becomes a lot more challenging as a structure to put together because it doesn't fit a lot of our standard patterns. Okay? Because you could be like, just because you open the can of worms, it's totally this structure, right? Yeah. Doesn't that still match? Oh, dang, it does. Is that going to have a different entropy? Yeah. So as you change the structure, your entropy will also change. The formula doesn't show you that structure. So you have to be real careful with interpreting those individual structural analyses because you don't know the structure very well. Okay? Whoop, what just happened? Quiz one, we already talked about that. Okay. Entropy of our system. So if we now go through and summarize what we've gone through across both today and the other day that we talked, we calculated an exothermic change for our butane. We noted the entropy increased for the combustion of butane. For the production of cement, we noticed that we had an endothermic enthalpy change, and we had a positive entropy change. Because a few students made kind of a simple mistake within this. I want to be real careful when we talk about this. Exothermic does not mean entropy increases. Right? Because endothermic showed entropy also increased. Those are separate topics. They are not tied to each other. Why are they being put into the same scenario right now? These are specific cases for that reaction. If I change the reaction, can I change how endothermic? An endothermic reaction could very well be a negative entropy. Okay? So don't start associating those things together. These are summaries of these particular chemical reactions. So it's tied very specifically to the reactions addressed here. Kind of, sort of? Okay. There's our summary slide. In this reaction, the products are energetically, are the products, I can't read the question, you read the question. It's one of the group things. Talk at your table real quickly. Let's talk through it a little bit. I did hear, well, maybe the products are actually more stable bonds. If they're more stable bonds, what happens to the energy of the products? Which means exothermic. It's not exothermic, it's an endothermic reaction. So looking at the energy of the bonds is not helpful. How do I make it happen? Okay, activation. How does the activation energy reached? How do I get my reactants to clear the activation energy? I put energy into the system. How do we get energy into our systems? You heat it up. Okay? So how can we possibly get this reaction to happen? We have to put a bunch of energy in to force the chemical reaction to happen so that we can go up in our energy. Kind of make sense? Okay. So if we're looking at just how entropy functions, entropy tends to go from lower to higher states. That's the natural order of things. So the example with pouring our cream into coffee, which you should never do, and if you think that you should do it, it's because you have bad coffee. Buy better coffee and you fix the problem. Okay? When you pour the cream in, what happens? Does the cream just sit at the bottom? No, it'll naturally swirl and fill the whole container. Okay? Another personal example, when I was a kid, we'd be allowed to get Kool-Aid or make Kool-Aid. We always had to make it because we buy it in bulk. Okay? You get just the sugar powder and then you had to make it. Okay? Except there was one rule. We were never allowed to stir it. And some people were like, well, why? Because my dad was an asshole. What happens when you don't stir it? It sits at the bottom. Does it just stay there at the bottom? It disperses, eventually, very, very slowly. Okay? So if we wanted Kool-Aid, we had to have the patience to wait for entropy to come and activate enough that we could get the whole solution to stir. I have plenty of memories, literally with my eye at counter level, looking at the Kool-Aid slowly dissolve into the system. Okay? Taught you patience, okay, or frustration, one or the other. Okay? So our substances will spontaneously mix. They'll move around. Okay? One of the things that's more interesting about this is that we can't unmix spontaneously. Okay? I can't pour the milk in and then wait at some point, even let's stir it around, let's make it all stirred so it's all mixed. And if I wait long enough, will the milk ever unstir? No. Same deal with the Kool-Aid. Okay? At no point are the sugar crystals going to come back out of the water. Once they've made it into that system, they're stuck in that system. That's an observation that we note when we consider entropy. Right? And in that process, what we're actually summarizing is the second law of thermodynamics. Right? A reaction or a process will be spontaneous if it results in an increase in entropy of the universe. So we can look at the entropy of the universe. The entropy of the universe is going to have two components. Okay? Whatever our reaction is and the surroundings. Okay? So you've tested some chemical reactions back in Gen Chem. If we mix an acid with a base, what happened in the lab to the container? Anybody remember? It's a long shot. I'm hoping for some really good memory, and I'm hoping you did the lab. When you mix the acid with the base, it gets hot. Right? That heat was released by the reaction. Where did that heat go? To the surroundings. And it got hot because you felt it. That's you are part of the surroundings. That's not the chemicals. Right? That heat dissipates out to the surroundings. Similar system when we're talking about our entropy systems is that if we're looking at our spontaneous reactions, our delta S for the universe will always be positive. Okay? So if we consider our exothermic and endothermic reactions, does the entropy of the surroundings increase or decrease in an exothermic reaction? What about an endothermic? So I like some of the discussions I'm hearing. We're talking about what's happening with our temperature. We're also talking about previous slides. That's a dangerous previous slide because what you're doing is the exact mistake I told you not to do. Those are only tied to the individual chemical reactions. So we got to be careful with looking at that slide. Okay, that specific chemical reaction. So if we look at the exothermic system, what's happening? The heat goes to the surroundings, which means the temperature is going up in the surroundings, which means what happens to all the particles in the surroundings? They move more. And if they're moving more, what happened to our entropy? It increased. And if we look at the endothermic reaction, all that energy went into the system, which means the temperature dropped outside in our surroundings, which then means our entropy decreased. Okay? The fun thing that can kind of come out of this relationship is this fun little equation. If we're looking at the entropy of our surroundings, it is directly related to the enthalpy of our chemical reaction. Okay? So I think it's still technically directly related. Okay? But when the enthalpy of our reaction goes up, what happens to the entropy? Yeah, this is hard. Okay? When our reaction, our delta H, let's look at a delta H for the exothermic reaction. What's the value? For an exothermic reaction, our delta H will be negative. So if we're looking at our equation, the delta H is negative. What happened to our entropy? I'm intentionally trying to hide that. For the exothermic, what was it? I heard it. It was positive. But if delta H was negative, that doesn't make sense. So that's why we have the negative in there. That negative shows how those two systems are now related. And if we have an endothermic reaction, our delta H is positive, but the entropy decreased, so I need that minus sign to account for it. Okay? We'll also note that it is heavily tied to temperature, okay, which is a fun little observation. Okay? And that observation, let's see, is it the slide? Not quite yet. Okay? So we get this system now where we can look at the relationship between exothermic reactions and changes in enthalpy and changes in entropy, okay? And talking about spontaneity. If we're looking at an exothermic reaction, what would our energy diagram look like? Our products are lower in energy than our reactants. Okay? If we added an endothermic line on this, where would our endothermic reaction, how would it change our energy diagram? The product energy would be higher. Which of these is spontaneous? Which one is more likely to occur? Exo. Why? Envision your material as a ball. If I put a ball here, where is it more likely to go? Is it likely to roll down, or is it likely to roll up? It's going to roll down. That helps to establish that kind of linking behind it. What does that do for us? Well, an exothermic reaction is more likely to occur. So if I have a negative delta H, what would I say? It's a spontaneous reaction. And if I had a positive delta H, I would have a non-spontaneous reaction.
That's the same regardless of the entropy in the system.
And that has nothing to do with the entropy of the system. Okay? All we're looking at now is the bond energies. That's it. Okay? But what we've now also added to this picture is that entropy can contribute to this as well. So what's spontaneous for our entropy? Should our entropy change be positive or negative in a spontaneous system? Does entropy go up or does entropy go down naturally?
Naturally goes up.
It naturally goes up, which means if I'm going to look at my delta S, when it's positive, the delta S contribution will say it is spontaneous. Spontaneous. When the delta S is negative, what happens? It's non-spontaneous. What we're trying to do is interpret some of those systems and their individual relationships. And this quadrant system sets up some interesting observations. For instance, if I have an exothermic reaction where the entropy goes up, it will always be spontaneous. Oh, missed it. What happens in the lower right-hand quadrant? It will always be non-spontaneous. Well, if it's always non-spontaneous, how easy is that reaction going to be to run? That's going to be a really hard reaction to go through and run. What about the other two quadrants? Okay. In one scenario, upper right hand, I say, well, it's spontaneous. Well, it's spontaneous when? When the enthalpy is more important than our entropy. That's what that system says. And the lower left hand, when does that reaction work? That reaction works when the entropy change is more important than the enthalpy change. Okay? That gives us some information and a little bit of context that we could start to play with. Okay? How does that end up getting played with? Are we good with it? I was just being a jerk trying to jump in pictures. Did anybody want a picture? Not of me, of the screen. No. Okay. Just checking. Someone went through, noted all of these changes, and realized that there has to be a better way to describe our potential energy system. It's not just bond energy. We also have to take into consider entropy in our energy diagrams. Okay? The person that was able to homogenize all this information into a single expression then has summarized some really important critical things. And because it's really important and critical, what happens? Their observation gets named after them. And we know that we encountered the Gibbs free energy. That Gibbs energy can now get defined in a few different ways. Okay? We already addressed one of them. Okay? Looking at how our overall energy of our system is related to the energy of our universe. Okay? We can also look at how the entropy of our surroundings is related to our enthalpy. And if we take those two pieces of information and we smash it all together, what do we end up with? We end up with this this super cool unified theory that now describes the delta G for all things. So if I want to talk about how two solutions mix, what happens to the bond energy? If I just mix two things, what's happening to their bonds? It's a good answer. Nothing. Nothing happens because all I did was mix them. Okay? That's a physical approach. But that mixing process could cause a change in temperature. That could cause a change in energy for the overall system. The enthalpy term drops out of my expression, and what I'm now left with is how entropy, did I say enthalpy right? The enthalpy term drops out, and my entropy term is now going to dictate how that system mixed. Is it only dependent on the entropy? That's a fun question. What do you think? Right? Hopefully we can say no, and we should say no, it's not dependent just on the entropy. Why? There's a temperature term within that system. Does that temperature term make sense to include in our system? Yeah. What happens when you heat things up? They move faster. Okay? And when they move faster, what happens to their speed of mixing? So that temperature will contribute to our mixing process just as much. So this system or this equation now becomes insanely powerful to us. And if we consider what we just looked at, that table, come on. Oh, because I got in this. What we can now go through and modify is representing our delta G. The delta G value we want should be negative. Okay, so in that upper left-hand corner, at all temperatures, we'll get a negative delta G. And if we think back to that table that we just filled in, where I said, did you want a picture of it? If you had that picture, you could look at it, and according to the enthalpy, we said our reaction was spontaneous. And according to the entropy, we said our reaction was spontaneous as well. Those both contribute to a negative delta G. How do those contribute to a negative delta G? Well, we've got that fun little equation up there. I don't need to know the number of the enthalpy change or the entropy change. I just need to know the magnitude, which direction. If enthalpy was negative, I should put a negative value. Minus, what's the value for my temperature? Can I have negative temperatures? Okay, and this becomes a fun kind of differentiation with our units. In degrees Celsius, we could, which means the temperature could be positive or negative. Would that mess with our ability to interpret this? Yeah, it would mess with it very severely, which means we need a temperature system that is always positive. That's Kelvin. And if we think back to the units that we used on entropy, what were those units? Joules, close, per mole, Kelvin. That's why the Kelvin was there. It's because it's going to show up in our expression up here. So our temperature will always be positive. It has no overall effect. What's our enthalpy, our entropy going to be? Well, it could be positive or negative depending on the system. If we're looking at the upper left-hand corner, what was our entropy? It was positive. So if I take a negative value and I subtract a positive value, what's going to happen to the size of my number? It's going to be negative. When? Always. There will never be a scenario where I can take a negative number and subtract a positive number and get something that is positive. That doesn't work. What happens if we look at the lower left-hand quadrant? What did we say? Well, the enthalpy was positive. Okay? And if I take a positive value and I subtract, what's going to happen? What would happen to the size of my positive value if I subtract something from it? It would get smaller. So could it possibly become negative? Ooh, it could be. But that lower right-hand corner said not spontaneous at any temperature. It had to be positive all the time. What was the sign on temperature? Positive. What's the sign on our entropy for the lower right-hand corner? Negative. It's a positive minus a negative, also known as adding two positive numbers. The distribution of that minus sign is going to ensure that no matter the size of the numbers, we will always get a delta G that's positive. What happens if we move into a different quadrant? Let's say the lower left. What did we say our delta H was? What did we say our temperature was? What did we say our entropy was? Is this reaction always going to be spontaneous? No. What's going to change it? This has to do with the magnitude of our entropy, okay? And, more importantly, the temperature. If that temperature value gets really, really, really big, when I multiply it by my entropy, I can make a number that's large enough that when I subtract, I go negative. Okay? So that quadrant is now spontaneous when what? When the temperature is really, really, really high. What happens in the upper right-hand quadrant? What's my delta H? Negative. Minus, what's my temperature? Positive. If I take a negative and subtract a positive, what's my sign going to be? Negative. So it would always be spontaneous, except what's the sign on the entropy in my upper right-hand quadrant? Negative. What's that negative going to do? And I now encounter this scenario of a negative and a positive. For delta G to be negative, to make it spontaneous, what has to be the magnitude of that positive value? Has to be really, really, really small. This usually trips up students. And the primary reason I think it trips up students is how many numbers did we use? None. What we used instead was just positive and negatives. Okay? And the positive probably wasn't the issue. The negative was the issue. You have to be real careful to distribute your negative appropriately in your formulas and interpret that correctly. Is that challenging? I would argue yes. I screwed it up all the time. Okay? I screwed it up until I wrote out a table like this and kept that in front of me whenever I was asked questions about thermodynamics. Because then I didn't have to deal with what's happening in each of those scenarios. I've already got it solved out and written, and I can now just navigate. So if you have trouble with your positives and negatives, I would argue what you should do is take this table and the previous table, where we addressed our delta H and S, being spontaneous or non-spontaneous, and tie that all together in one glorified table. And because you're allowed a cheat sheet, that would be a table I would include on my cheat sheet so that I don't have to remember all of those negatives and positives that I know I'm personally bad at, and I can just use the table. Kind of make sense? Cool. So we've got this system, right? Will this reaction happen spontaneously? Right? And you'd be like, well, I don't know the delta H. You do know the delta H for this reaction because you have notes and you solved it on Tuesday. What was the delta H for this reaction? Subtle hint, it was positive. What was that? 178.3. Okay. We also know the delta S. Why? We solved it today. What was our delta S? Positive 471.4 joules per mole Kelvin. Didn't we solve it?
No, we solved the other one. We solved the combustion reaction.
Should make you calculate it again here in a second. That would be kind of embarrassing. So now I'm curious. Maybe she just gives you the value. 160 sounds familiar, but maybe we didn't calculate it. What was our delta H? Let's just go with signs. Positive. What was our delta S? Positive. We follow our quadrant system. Delta H positive puts us on this line. Delta S positive puts me on this line. Where do they intersect? that lower right-hand corner. When we talked through this reaction, and I said, how could this reaction happen if it was endothermic? What did you all say? High temp. Oh. Isn't that neat? There it is. You just predicted a high temperature. There's our system. That was fun. Was that my next class? All right. How could we work with this or manipulate this? Okay. Well, what we could now go through and do is we could calculate the delta G for the reaction at different temperatures and see what happens. Okay. So we would need those numerical values. Are those numerical values things that you will be given? Yeah, maybe. Or you'll calculate them first. Okay, so you could be given a table of standard entropy values so that you could calculate what your change in entropy was, so that you could then plug the change of entropy into our delta G expression to then figure it all out. So how do we go through and set this up? Well, our delta G equals 178.3 kilojoules per mole minus, I don't know why we did a different color. I know why I did a different color. Let's make that minus stand out. Minus our T. What's our T? 25 degrees Celsius, right? Plus 273. And if you're like, I don't remember how to calculate Kelvin from degrees Celsius, that's quite all right. Not a big deal. What should you do? Put that formula on your cheat sheet so that you've got access to it when you need it. So when we do that math, what do we get? It's 298, right? 298 Kelvin. What's our entropy? Okay. 160.2. 160.2 times 300 is a big number. What happens when I take 178 minus a big number? What am I going to get? A negative value, which would say this reaction is spontaneous. I thought we said it's not spontaneous. We said it had to be a high temperature. Is 25 degrees a high temperature? No, 25 degrees is not a high temperature. 1,450 is a high temperature. What did we screw up? What are the units on that 160.2 that Mike suspiciously did not include? Joules per mole times Kelvin. What happens? Our Kelvin unit will cancel just fine. When I now go through to run this calculation, I can't run the calculation because kilojoules don't subtract from joules because they're different units. I have to run through a conversion first. When I run through that conversion first, depending on how confident you are in your conversions, you could just shift your decimal and it's now 0.1602 times our 298. That number is now not very big, so that when I take my 178 minus that number, I get a positive value. That matches our observation. So does that mean you need to track your units? Since it took such a long time to find that unit mistake, I'm going to say yeah, you should track your units really, really well to ensure you don't make a simple calculation mistake like that. All right? What happens when you go to 1450? Well, you'll just change this number, our temperature number, to 1450 plus 273. And what's going to happen to our delta G? It's going to switch to being negative, and a negative delta G is spontaneous. Neat? Cool. Where I want to leave you is a little bit of a cliffhanger. What is the minimum temperature required for the reaction to happen spontaneously? So now it's not plug and chug and say positives and negatives. I want to know the temperature, the exact temperature at which I switch from being positive delta G to negative delta G. All right? You have to set up your own system to navigate how you would go through and do that. We'll start class Tuesday with that process if you haven't already figured it out by talking to other people.